Ready for a deep dive into something we experience constantly but rarely think about.
Always up for a challenge. What do we got?
Gravity. From how it feels right here on Earth to its role shaping the whole universe.
Gravity. Keeps our feet on the ground. But yeah, it's so much bigger than that.
Exactly. So let's start basic. That feeling of things falling down, the effort to climb uphill, those are our first experiences with gravity, right?
Absolutely. Like built-in intuition. But our understanding's come a long way since just dropping stuff.
True. So Galileo, he was one of the first to really dig into why things fall as they do. What was his big breakthrough?
Well, he realized that every object, no matter how heavy or light, accelerates toward Earth at the same rate.
Wait, so you're telling me a feather and like a bowling ball would fall at the same
A
speed?
heat vacuum, absolutely. Air resistance messes things up in everyday life, but Galileo figured that out using inclined planes, slowed the fall down enough to take accurate measurements.
Huh. That's pretty counterintuitive. Did this new understanding affect how people saw the universe as a whole back then?
Huge impact. Before Galileo, the main model was Ptolemy's geocentric view.
Ah, that's the one where everything revolves around the Earth, right?
Exactly. Earth at the center, everything else in perfect circles around it. Sun, planets, the whole shebang.
Perfect circles. Seems kind of simplistic looking back.
Well, for its time, it was pretty complex and predicted planetary positions decently. But yeah, the circle thing, not quite right.
So who came along and shook things up?
Before Copernicus popularized the idea in Europe, astronomers like Aryabhata from India were already talking about a sun-centered system. Then, Copernicus in the 16th century, he really pushed this heliocentric model, sun at the center, challenging the whole established view.
Talk about a controversial idea.
Oh, absolutely. Major religious and philosophical implications. This was not a small shift.
Makes sense.
Yeah.
So even with the sun in the right spot, did they figure out how the planets actually moved? Those perfect circles couldn't have lasted, right?
You're right. Enter Tycho Brahe, incredibly precise astronomer, obsessed with observation, collected decades of data on planetary positions.
Dedication. But I'm guessing he wasn't the one to figure out planetary motion itself.
Correct. That's where Johannes Kepler, his assistant, steps in. Brilliant mathematician. He looked at all Brahe's data and found the real patterns hidden in it.
Ah, and that's where Kepler's 3 laws come from, the ones I vaguely remember from physics class.
Yep. Revolutionary stuff. His first law: planets don't move in circles, but in ellipses, with the sun at one focus point.
Okay, ellipses. Need a refresher there. How do those work again?
Think of it like this. You got a circle, one center point, ellipse, 2 foci. Imagine pushpins at those foci, loop of string around them. Use a pencil to pull the string taut, move it around.
Yeah.
You'll trace an ellipse.
Ah, okay, that makes sense. But do planets move at a constant speed on these elliptical paths?
That's Kepler's second law. Speed changes throughout the orbit. Faster closer to the sun, slower further away. Described by the law of areas, an imaginary line from planet to sun sweeps out equal areas in equal times.
Wow, elegant way to describe such complex motion. And his third law, that's got something to do with the time it takes to orbit, right?
You got it. Connects a planet's year, its orbital period, to its distance from the sun. Further out, longer the orbit. And there's a precise mathematical relationship there.
Just from watching planets, Kepler figured out these fundamental laws. Incredible. Did this give any clues to why the planets behave this way?
Kepler's laws were purely from observation, but they hinted at some universal force controlling the whole dance.
Which brings us to, drumroll, Isaac Newton. And that famous apple story, right?
Yep. The story goes, Newton sees an apple fall and thinks, could that same force pulling the apple down also be keeping the moon in orbit?
Apple to the moon. That's quite the connection.
Seems like a leap, but think about it. Moon's not just floating. It's constantly being pulled towards Earth, stopping it from flying off. Newton realized the moon's acceleration, though smaller than the apple's, fit this idea of a force weakening with distance.
So he linked gravity on Earth to the motions of celestial objects. Big deal.
Huge. That led to his universal law of gravitation. Any 2 objects in the universe attract each other. Force is proportional to their masses and inversely proportional to the square of the distance between them.
So not just apples and moons, but everything.
Exactly. Apples, moons, planets, stars, galaxies. This law gives the universe structure.
Okay, walk me through that law. So the force is proportional to the masses, meaning more massive object, stronger the pull.
Exactly. Earth pulls us down way stronger than, say, a pencil does. Earth's mass is huge E compared to the pencil.
And the distance part.
Yeah.
inversely proportional to the square,
Hmm.
meaning the farther apart, the weaker the force.
Exactly. And it weakens fast, double the distance, force is 4 times weaker, triple it, 9 times weaker.
That's why we don't feel the sun's gravity pulling us away from Earth, even though the sun is way more massive, right?
You got it. Distance matters. Sun's pull on us is tiny compared to Earth's.
Mind blown. So Newton figures out this law, but how do we know how strong gravity actually is?
Henry Cavendish, he came up with this brilliant experiment. Used a torsion balance, a super-sensitive seesaw basically, measured the tiny twist caused by gravity between lead spheres. This let him figure out G, the gravitational constant.
So G tells us the strength of gravity, like a universal setting.
Exactly. Fundamental constant, like the speed of light. And knowing G let us do something amazing, weigh the Earth.
Wait, we can weigh the Earth. How?
Remember Newton's law? We know how fast things accelerate due to gravity here on Earth, 9.8 meters per second squared. We know Earth's radius. Cavendish gave us G. Plug it all in, you can solve for Earth's mass.
Wow, we use gravity to weigh the Earth. Genius.
It all started with that apple. Now, we've talked about gravity pulling us down, but what if we go higher? Does it weaken?
Good question. I'm guessing the further we are from Earth's center, the weaker the pull.
You got it. It's all about the distance. But what about the opposite? What if we go deeper into the Earth?
Now that one's tricky. Wouldn't the force get stronger closer to the center where all that mass is?
It's counterintuitive, but no. As you go deeper, the mass above you starts counteracting the pull from below. At the very center, you'd have mass all around, pulling equally in every direction. Forces cancel out.
Like a gravitational tug-of-war ending in a tie.
Perfect analogy. Now, in reality, Earth's not perfectly uniform, so it's more complicated. But the general idea holds. Gravity's strongest at the surface weakens as you move up, over, or down.
So cool. We've talked about strengths changing with distance, but what about the energy aspect of gravity? That's always intrigued me.
You're talking about gravitational potential energy, stored energy based on an object's position within a gravitational field.
So the higher you lift something, the more potential energy it has.
Exactly. You're working against gravity to lift it. That's why carrying groceries upstairs gets harder the higher you go.
Tell me about it. What happens to that stored energy if you drop something?
Well, don't try that with your groceries, but as it falls, potential energy turns into kinetic energy, the energy of motion.
Makes sense. Is there a point where an object has enough potential energy to completely escape Earth's gravity?
There is. That's called escape speed. The speed needed to break free and never come back. For Earth, it's about 11.2 kilometers per second.
Zooming really highlights how strong Earth's hold is.
It does. And think about the moon. It has no atmosphere because its escape speed is much lower, only about 2.3 kilometers per second. Any gas would just drift it off into space.
Huh. I never thought about it like that. So objects fall to Earth, can escape. What about the ones that stay in orbit? How do satellites manage that?
It's all about balance. Gravity pulls them down, but their forward motion keeps them from hitting the ground. Imagine throwing a ball so hard that as it falls, the Earth curves away beneath it at the same rate. That's basically an orbit.
So satellites are constantly falling but also moving forward.
Exactly. They're in constant free fall, but their speed and altitude are just right to keep them from crashing.
How do they find that perfect balance?
It's all about speed and altitude. Further out, weaker gravity, so they need to move slower to stay in orbit. Closer in, need more speed.
So Kepler's laws apply to satellites too then?
You got it. Those laws describe any object orbiting another under gravity's influence. Planets around the sun, satellites around Earth, same basic principles.
So cool. What are some of the ways we use satellites, practically speaking?
They're essential these days. Communication, navigation, weather forecasting, observing Earth, scientific research, even military applications.
Amazing how much we rely on these things constantly falling around our planet.
Sure.
We've talked about kinetic energy, potential energy.
Yeah.
How does energy fit into the whole picture of an object in orbit?
Great question. A satellite has both. Kinetic energy from its motion and potential energy from its position within Earth's gravitational field.
A mix of both. Does one type dominate?
What's fascinating is that for a stable orbit, the total energy is always negative.
Negative. How's that possible?
We define zero potential energy as being infinitely far from Earth. Any object bound to Earth will have negative potential energy. It's relative.
Ah, so a satellite's bound to Earth, its total energy has to be negative. If it were positive, it would just fly off, right?
Got it. That delicate balance keeps things in orbit.
This is incredible.
It is. Back for more gravity fun. We're about to take things up a notch.
Definitely. Last time we were mind-blown by how energy keeps satellites in orbit. It's amazing how everyday things like throwing a ball help explain what's happening in space.
Right. Speaking of earthly gravity, let's revisit how its strength changes as we move around. We talked about how it weakens as you go higher.
Yeah, and also as you go deeper into the Earth. That one was crazy.
Total mind bender. To picture it, let's imagine a tunnel straight through Earth's center. Drop something down it. What do you think happens?
Okay, it would fall towards the center. But then, we would just get stuck there.
Good question. Ignoring air resistance and Earth's rotation, it wouldn't get stuck. It would oscillate back and forth through the tunnel.
Oscillate, like a pendulum.
Exactly. Falls towards the center, speeds up, passes the center, slows down as gravity pulls it back towards the other side.
So keeps going till it reaches the surface on the other side.
Yep, then stops momentarily before being pulled back towards the center again, back and forth through the core.
Wow. But wouldn't one full trip take, like, forever?
It would take some time, calculated to be about 84 minutes.
84 minutes.
Yeah.
Wait a second, isn't that roughly how long it takes a satellite to orbit Earth at a really low altitude?
Bingo. And that's no coincidence. There's a deep connection between that oscillation through Earth and a low-altitude satellite's orbit.
Now, I'm really intrigued. What's the connection? How can a straight line through Earth relate to a circular orbit in space?
It's all about how gravity acts in both cases. The force pulling the object towards Earth's center is proportional to its distance from the center.
So even though one's moving straight, the other's in a circle, the physics is similar.
Exactly. That's why they have the same period. Different phenomena, same underlying physics. Pretty cool, huh?
It's like the universe is following a secret code, and we're just starting to crack it. We've talked about gravity here and an orbit, but now I want to zoom out. How does gravity shape the universe on a grander scale? What about galaxies?
Now we're talking. Gravity is the architect of the universe. It forms stars, galaxies, even the large-scale structure of the cosmos.
Okay, let's start with stars. How does gravity create those?
Stars are born from massive clouds of gas and dust floating in space. These clouds are huge, and within them, some areas are denser than others.
So it's not all perfectly evenly spread out.
Nope. And those denser spots, gravity starts pulling matter in those regions towards each other.
Like a cosmic sculptor, pulling everything together.
Perfect analogy. More matter gets pulled in, gravity strengthens, the cloud collapses.
And as it collapses, does it just shrink forever?
As it collapses, the core's pressure and density skyrocket, temperature goes way up. Eventually, it gets so hot and dense that nuclear fusion starts.
Nuclear fusion, like what powers the sun?
That's it. Hydrogen atoms fuse to form helium, releasing massive amounts of energy. Boom, a star is born.
Wow, gravity literally kickstarts the creation of stars.
It's the fundamental force behind it all. Brings matter together, creates the conditions for fusion, ignites these celestial furnaces that light up the universe.
Mind-blowing. From something as simple as gravity.
Yeah.
But its influence doesn't stop there, right? It shapes galaxies, too.
Absolutely. Galaxies are massive collections of stars, gas, and dust, all orbiting a central point.
Right, those swirling, majestic structures. So how do they form?
Just like stars form from collapsing gas and dust clouds, galaxies come from even larger clouds, but on a much grander scale.
Same process, just way bigger.
Exactly. Gravity pulls everything towards the densest regions, causing the cloud to collapse and spin.
And as it spins, it flattens out into those spiral disk shapes we see.
That's one type, the spiral galaxy. There are also elliptical galaxies, more rounded, and irregular galaxies with no defined shape.
So gravity shapes these vast structures, but it also holds them together, right?
Yeah, you got it. The gravitational pull between all the stars, gas, and dust keeps the galaxy from flying apart.
It's like cosmic glue, holding everything together.
Love that analogy. And it's not just within galaxies. Gravity also dictates how they interact with each other.
Wait, galaxies interact? I always pictured them as isolated islands in space.
Space is vast, but galaxies are so massive their gravity extends far. They can influence each other across incredible distances. They can collide, merge, even tear each other apart.
Galaxies colliding, that sounds intense.
It's not a head-on crash, more like a slow dance. Their gravity distorts their shapes, triggers bursts of star formation as gas and dust get compressed.
So galactic collisions are actually creative events.
Yeah.
Leading to the birth of new stars.
Precisely. Over billions of years, these collisions reshape galaxies, sometimes merging them into even larger structures.
Wow, it's amazing to think about these seemingly static objects constantly moving and interacting. We've talked stars, galaxies. What about the universe as a whole? Does gravity shape its overall structure?
It's the architect of the cosmos. When we zoom out to the biggest scales, galaxies aren't randomly scattered. They're organized into clusters, superclusters, filaments, and voids, almost like a cosmic web.
So there's a structure to the universe. It's not just chaos.
Definitely not. And guess what's responsible for this grand design?
I think I have a pretty good idea. Gravity.
You got it. Gravity, over billions of years, pulls matter into these vast, interconnected structures, leaving behind huge empty spaces, the voids.
So gravity shapes everything, from tiny planets to these immense cosmic structures. It's incredible.
It really highlights the power of this fundamental force. And what makes it even more fascinating, we're still figuring it out. There are so many mysteries about gravity, especially how it fits with the other fundamental forces.
Now you've piqued my curiosity. What are some of the big unanswered questions about gravity?
One of the biggest is how gravity interacts with quantum mechanics, which describes the behavior of matter at the tiniest levels.
So there's a disconnect between our understanding of gravity on large scales and at the super small scale.
Right. Our theories of gravity, like Einstein's general relativity, work incredibly well for large objects, but they break down when we try to apply them to the quantum world.
So we have two incredibly successful theories, but they don't get along when it comes to gravity.
Exactly. And that's a huge challenge in physics today, unifying these two pillars of our understanding.
This is getting pretty complex. Can you break it down a bit? What's the main clash between these theories?
Sure. General relativity describes gravity as a curvature of space-time caused by mass and energy.
Ah, right, like the bowling ball on a trampoline. The ball warps the fabric, and that's gravity.
Exactly. Works great for planets and stars. But then we have quantum mechanics, where things get fuzzy and unpredictable.
Particles can be in multiple states at once, their properties are uncertain, and even observing them changes things.
Right. The quantum world has its own rule book, and it doesn't mesh with the smooth space-time of general relativity.
So how do physicists try to bridge this gap?
The million-dollar question. They're searching for a theory of quantum gravity, one that can describe gravity in a way that works with the strangeness of quantum mechanics.
Are there any promising candidates for this theory?
Several approaches, but one of the most well-known is string theory.
String theory. I've heard of it, but it always seemed really abstract.
It is complex. It proposes that the universe isn't made of point-like particles, but tiny, vibrating strings.
Like little pieces of string.
Not exactly. They're incredibly tiny, much smaller than anything we can see. And the way they vibrate creates the different particles and forces we observe.
So how does this explain gravity?
One of the ways these strings vibrate is thought to correspond to the graviton, the particle that carries the force of gravity.
So gravity itself is made up of these tiny vibrating strings.
That's one interpretation. And string theory might offer a way to bring gravity into the quantum world mathematically.
Fascinating. Is there any evidence to support string theory?
That's the tricky part. These strings are so tiny, it's incredibly hard to design experiments to detect them.
So it's still very theoretical.
Yes, but it's an elegant theory that could revolutionize our understanding of the universe.
Sounds like we still have much to learn about gravity at all scales.
Absolutely. And that's what keeps this field so exciting. There's always more to explore, more to discover, more mysteries to unravel.
Welcome back to our deep dive on gravity.
We've been on quite a journey, haven't we?
For sure. From feeling gravity's pull here on Earth to exploring the mind-boggling concepts of space-time and quantum mechanics.
And that big mystery, right? How to fit gravity into the quantum world.
Exactly. General relativity and quantum mechanics. Those two giants of physics. They just don't seem to play nice when it comes to gravity.
Like trying to mix oil and water. They just don't want to blend.
Can we dive a bit deeper into that conflict? I'm still trying to wrap my head around what makes them so incompatible.
Sure. General relativity sees gravity as the smooth, continuous curvature of space-time.
Ah, right, like that bowling ball on a trampoline, warping the fabric of space-time.
Exactly. That model works incredibly well for big stuff like planets and stars. But then we zoom in to the quantum level.
Where everything gets fuzzy and uncertain, right?
Precisely. Quantum mechanics tells us particles can be in multiple states at once, their properties are all blurry, and even looking at them changes things.
It's like a completely different set of rules down there.
And those rules just don't mesh with the smooth geometric picture of gravity from general relativity.
So how are physicists tackling this problem? How do we bridge this gap?
Well, they're searching for a theory of quantum gravity, a theory that can describe gravity in a way that works with all the weirdness of quantum mechanics.
Makes sense. Are there any frontrunners in this search?
There are a few promising avenues. One of the most fascinating is loop quantum gravity.
Loop quantum gravity. Haven't heard of that one.
It's a pretty radical approach. It tries to quantize space-time itself, breaking it down into tiny, discrete loops.
So instead of space-time being this smooth fabric, it's made up of these little building blocks.
Yeah. Exactly. It's like imagining space-time woven together from countless tiny loops, like a chainmail armor.
I like that visual. So how does that help us understand gravity at the quantum level?
In loop quantum gravity, the force of gravity emerges from the interactions between these interconnected loops.
So instead of smooth curvature, gravity is coming from the dynamics of these fundamental loops.
That's the idea. And it suggests that spacetime itself has a granular structure at the Planck scale, the smallest possible unit of distance.
So there's a limit to how small space-time can get, like a fundamental resolution limit for the universe.
Exactly. Quite a change from the classical view of spacetime as a smooth, infinitely divisible thing.
This is all so mind-bending. But is there any actual evidence for loop quantum gravity?
Like string theory, loop quantum gravity is still largely theoretical. Testing it directly is really tough. The Planck scale, where these quantum gravity effects would be noticeable, is way beyond our current experimental reach.
So it's a work in progress, but a very exciting one.
Absolutely. And just one of many paths physicists are exploring to understand quantum gravity.
Well, it's clear that gravity is a force with endless layers to uncover. Always new insights and challenges popping up.
It's what keeps science so captivating, that drive to understand the fundamental laws of the universe.
This deep dive into gravity has been an incredible journey,
I've enjoyed exploring it with you.
and we hope our listeners have too.
If there's one thing to take away from all this, it's a sense of awe and wonder at the sheer power of gravity.
From the tiniest atom to the largest galaxy, gravity connects us all.
So next time you see an apple fall or look up at the stars, remember the force at play.
And never stop questioning, exploring, and searching for a deeper understanding of our universe.
Until next time, keep those minds curious and keep looking up.
And that's a wrap on our deep dive into gravity. Thanks for joining us.